Welcome to Mathematics with eSums here and derivatives and partial derivatives. My name is Nate Nessler and this is for Hyperactive Studios. Now we use this kind of mathematics all the time for doing 3D animation and for graphics and games and such. And we're going to have to dive into some of this. Now I'm going to keep this as simple as possible because if you ever look at some of these mathematics books and these textbooks for their derivations and such of the formulas, it gets really complicated very quickly. But it's really quite simple. It's been made complicated, but it's really quite simple for how to do this stuff. Let's look at eSums for starting off, or eSummations. And an eSum is just going to look like a Greek, well, the Greek eSum. It does a Watch camp. Here we go. Let me draw it, because if I don't draw it, it's not doing it in the program here, so you're not going to know what it looks like otherwise. But essentially what it is that we do it from a range. It's like a for loop in programming, and we just go from a range from, like, say 0 to 5, right? And then we compute through this formula values 0 through 5 for x, right? So we have 0 here plus 5 gives me one number, and I'll prove this too. We don't have to worry about, we don't have to wonder if this is truth or not. 0 plus 5, right? Because I'm passing in a 0 here, so we're going from 0 to 5, passing in through x, right? So according to this formula, it's going to be that, right? And it's a summation, right? So let me go ahead and put parentheses around this to help, make it graphically more straightforward. Let's put it that way. And I'm lazy, so I'm going to start copying and pasting. Yeah, you can do that with math. It's fun. All right. So I'm going to change that to a 1 because, right, we're counting up, right? I can get a little bit faster with this if I just do that right there. Alright, let's start adding on as we go here. And then we're just doing this throughout each value, going from 0 to 5 for x. And we're just adding it up like this. Alright, and I'll give us 5 right there. Great, semicolons, shift enter, 45. There we go. It's the exact same thing. There's the expanded mathematical computation that was done throughout this to get the same thing. So that's exactly what's happened. It's gone 0 through 5 here through x, over and over and over again, adding up this little formula together, adding each resultant value from each one, or shall I say the value you get from each computation here. So for instance, if I pass 0 into x plus 5, I get 5. So 5 plus the next computation times the next computation. I mean, sorry, not times, but plus. Sorry. The computation here from the formula plus the next computation plus the next one plus the next one plus the next one plus the next one until you get all the way to the end. Okay. There's actually ways of using derivatives in order to find infinite solution with the eSum. I'm not going to get into it, but yeah, there's ways of doing that. That's too. We're not going to do that in this video, that's for sure. Alright. Anyways, you can add all these together and you'll get your final summation. So this is the same way a for loop works. So by when you look at a math eSum, you're really thinking pretty much like for loop in programming. So this makes it real easy for you to find a combination. It's really weird. Okay. All kinds of weird stuff's going on here. Okay. It's freaking out on me. Okay. Alright, there we go. So, alright, so eSum, right? It's gonna look like this. And you've probably seen them before. And if you haven't, cool. Well, that's what they look like. And that's an eSum. And you'll say something like, oh, in this case it'd be x, right? Because that's what we're working with. And I really need a much thinner pen than this, so let me give myself a I think I'm bogging the computer down too much. This is a fast computer, but still in recording. Alright. So say I do an x here, and we say that x is equal to, it's an ugly x, but I don't care, is equal to, no, let's not do that. X is equal to 5 in this, example. I'm drawing with my mouse. Have mercy on me. All right. No, I'm sorry. That wouldn't be. That'd be x equals 0, and it's going to go to 5. That's supposed to be a 0. Use your imagination. This is why you don't do art with graphics with a mouse. Use a graphics tablet for that. Alright, so here we got a 5 here. Ah, yes, 5 in all its glory. Yes. Alright, and then we have our x here. Alright. And our, whoa, what am I doing? Alright, I'm going to do an x plus 5 here. Alright, and then that's how it would be written up more formally on a piece of paper, if you will, and that would be the formula for ESUM. But in the program, Maxima, which displays it better than the others, in my opinion, it's written out like this. And I even did an expanded form of this to show you with running it as a function here. So here I'm putting in some unknown function, and if it's plugged in, of course, it would compute it. But 5 is getting passed in through the function to be computed separately. And so I'm showing and proving that yes, it is done iteratively here through this process, meaning that it's computing it 5, 4, 3, 2, 1, 0, bam. And computes it throughout all those computations for each one. So 45. This is exactly how I said it was computed, and here it is being shown in formula form of it being computed for some function g with variable x as its dependent, where x is independent of g. Anyways, so here I'm showing off x squared and the graph for x squared, and so that's the summation. Sorry. You could have far more complicated formulas of this, but it's just this simple. You're taking in some value here, starting at some value, and you're ending at some value, and you're going through all those values as you compute each formula and adding each result to each other. That's it. That's all there is to it. There's nothing more than that. Just like this example here. We're passing in the numbers and adding them together one by one by one until we get the whole thing. You do the same thing with a for loop. If you're familiar with programming, you have x plus 5 here. You do a for loop where x is your going from 0, starting x value at 0 and going to 5, and you just loop through the thing and then adding it to its self. You know what I mean? Like some summation or something like that. Like say you have a sum in there and just keep adding it to itself for the sum, and it's initialized at 0 before you went to the loop. Bam! There you go. You got the same thing as an ESUM. Exactly the same thing, and that's the programmatic way of doing that one. Kind of cool part though, if you're sitting there messing with Sage, since you have the Python there, you could literally write this up as a for loop and compute it and see the exact same result as what you would get with the eSummation calculation. So that's kind of nice, and kind of cool way of doing that. So just to show you. I mean, well, I'm not going to show you that one, but just to tell you, that's something you could do since it's using Python. Alright, so we have our x squared here, and this is our graph. Now if I take the derivative of this, now how do we do a derivative? It's insanely simple. You'll look at textbooks, it's incredibly complicated with a limit going to infinity, blah blah blah, all this stuff. Okay, so that gets complicated, but it's actually quite simple. You just use the power rule, and then you can solve it very quickly and very easily off the top of your head. And it's so ridiculously simple. It's it's not even funny. I mean, it's almost ridiculous how easy it is. So what we do is we subtract 1 from the power. And well, first, before we do that, we multiply the power times the coefficient in front of the x here, in front of the variable. Basically, the number sitting here in front of the variable, right? So 2 times the invisible 1 that's sitting right here in front of the x here is going to make this 2x, and then I'm going to subtract 1 from the power of 2 after doing that. It's going to leave me 2x to the 1 to the power of 1, which just leaves me with 2x. I mean, so that makes it easier to write it. So it becomes 2x. And check it out. If I take x squared and do the derivative of that, it's going to give me 2x. That's it. It's that simple. I have it written up here also. But it's fairly straightforward. I'll tell you what, I'll even zoom in a little more here. Hopefully that makes it a little easier to read. But that's all there is to it. It's quite simple and pretty straightforward. And that's really nice about derivative. Now you could have a really long, complicated formula where you have like x to the third, like 2x to the third or something like that, you know. And if you took the derivative of that, I mean like this huge long thing, you could do that. But if I took the derivative of that, right, it'd be 3 times 2 is going to be what, 6, right? And then 1 minus 3 is going to be 2, so I'm going to have what, 6x squared. You know, that would be my derivatives. Like I said, you can literally just do it in your head. It's that easy when you see how to do it. It's not bad. Here I did what I was talking about, x to the third. Here I took the partial derivative of it. Check it out. It's 3x squared, right? Why? Because we have 3 times the invisible 1 here. Bam. There we go. It becomes 3. And 1 minus the 3 up here gives me 2. So I have 3x squared. There we go. A more fancy example. Well, this is partial derivatives. Hold on. We'll do that later. Just hold on there. Alright. So we're going to go back over here to the happy land of simplicity. Alright, so here we are. We took the derivative of x squared and we got 2x. Great. Now, we can find the tangent to our curve. And this is really useful, particularly for 3D graphics on a regular basis, because you'll have to find all kinds of times you'll have to find tangents. For tangents to curves, tangents to surfaces, faces, on a model, I mean bitangents, binormals, etc. All this stuff. So tangents are quite important. So let's have a look at how to do a tangent to a curve real quick, because it's useful to know. Alright, so slope-intercept form. Here it's going to be y equals mx plus b. Now you've seen this from way back when, from geometry and algebra 1 and 2 and all this stuff. So this is pretty far back. It's simple stuff here. Point slope formula here, we have y minus y1, where y1 is a value from a point. And then m, remember m is your slope. Don't forget that, m is your slope. And then times x minus x1, where x1 is a value from a point. So for instance 2, 4, right? 2 would be for the x here, and 4 would be for this y1 here, right? So you'd have y minus 4 equals m times x minus 2, in parentheses. So there you go. That's how the point slope form works there. So we need to find the line tangent to x squared at x equals 2. For instance, it doesn't have to be x equals 2, it could be something else, but we just chose x equals 2. Okay? It's just something you just pick. Of course, if you're doing programming or something like that, you would have a particular probably reason why you'd have a certain value you'd use here or there. So, it's just whatever value is going to be used at some point in time that you're going to do a tangent to that point. So it won't just be random for you then. It'll make sense when you're doing it. But for now, we're just picking something random because, well, we don't really have any reason for selecting it otherwise. So we're just going to select randomly at this point. We found the derivative of x squared as 2x, just as above. And then since x is equal to 2, then we can find the slope of the tangent line, which is, using this formula 2x, which is the derivative. So if we take the derivative of a formula, we can find our slope here. So 2 times 2, because if we put in 2 for our x here, and we multiply 2 times that, we get 4. So our slope for m is 4. So our, 4 here or 4 here, however you want to look at it. That's our slope. Alright. Then the slope of the tangent line is, okay, so I already did that. Great, now you need a point shared on the original curve for x squared. So that means we need to calculate, that point being shared. Alright? So that's going to be important. So since we know that y equals x squared and that x equals 2, then we need to solve for y. Does that make sense? So if we have 2 in here and we're taking it to squared, 2 squared is 4, that gives us y. So we know our x is 2 and that means our y is 4. So that's very useful here. So again, y equals 2 to the second power here gives us y equals 4. And then now we know our point is 2 for the x because that's what we plugged in, and then 4 for the y because that's what we solved and got 4 for y here. Is now our point, since we know that both x and y, since we know what they both are, here for this point. Now we can use the point slope formula, which is this one right here. That's the point slope formula. Okay, so we just plug in these values, right? We got our 4 here, so we're going to plug in our 4 for our y1, and then we're going to plug in our 2 for our x1, right? Because that's the x value and that's the y value for our point. That's why it's called the point slope formula, because we're using a point in there. And then we already got our m value for our slope, and so there we go. So there's our slope. Awesome. And then we end up with y equals 4x minus 8 plus 4 gives us 4x minus 4 for our resulting value. Because of, well, yeah, you take 4, add 4 on both sides, that's going to eliminate this minus 4, it's going to put a plus 4 on this side, right? Distributive property here. So 4 times x and 4 times negative 2 as we distribute it through these values inside of these parentheses. So that gives us 4x minus 8, right? And then plus 4, because it was, adding 4 to both sides. And then that leaves us with, once you add 4 plus negative 8, you're going to get negative 4. And so we have 4x minus 4 equals y. And there we go. So awesome. That gives us a tangent to the curve at the point of 2, 4 on the x squared formula. So, and we use derivatives to find that. Awesome. So with this, we graph it, and exactly what we get. See, so at this point here, we end up with, at 2, 4, we end up at this point where this tangent line hits only one point on the x squared, and it hits exactly 2, 4, and nothing else. Now it's important to notice something. The closer we are to the point 2, 4, the more accurate the tangent value is. The more you move away from that point, further and further, it becomes less and less accurate. So if you're doing a formulation or calculation based off of a tangent from a surface, the further and further you go away from that main point, the more inaccurate it is going to become. So be aware of that. And maybe that's to your benefit, but that's something you have to know and understand by looking at this. And you can see that, yes, that is exactly what's happening. As I move away from 2, 4, it is becoming less and less accurate. And by saying less and less accurate, meaning that this line is not following with this curve more and more as it moves. So that's important. All right. So let's look at one other thing, and that is going to be partial derivatives. Okay, so just like we could take derivative for a formula made of x's, like x squared plus 3 squared or something like that, just as an example, I could get a little fancier with this real quick before I start diving into the partials. But I could sit here and say diff right here and then open close parentheses, and then I could say comma x comma 1, so because I only want to do one derivative, because if I sit there and tell it, it will keep doing more and more derivatives. Oh, as a side note, you can take the derivative of a velocity formula and get the acceleration formula, and you can take the integral of an acceleration formula and get the velocity formula. I'm not going to get into that. That's not doing that right now, but you can do it for all kinds of stuff. It's really useful. So these integrals and derivatives, integral is the opposite of a derivative. So as you can go like from this, go for that derivative, you can go back and get the actual original curve from by taking an integral of a formula, which is very interesting and very cool. Integrals are far more complicated, and we're not going to touch them with a 10-foot pole in this series. So maybe eventually later on we'll get into it. I don't know. It would have to be many videos to cover integrals, as it is pretty much what entirely Calculus 2 is made of. And so it pretty much have to be a series completely on Calculus 2, covering every aspect of it for the most part in order to cover integrals. Integrals are for the most part barely even touched on at the end of Calculus 1. At Calculus 3 it's more conceptual, but at Calculus 1 it's nothing but going brute force through all the mathematics through integrals, and you really have to, it would really require an entire series on integrals in order to cover it, to actually make sense of it. So my apologies, but I'm not really going to dive into it on this video. Alright, so I have, I don't know, 3x to the third maybe. It would so help if I did a multiply there and put x. And then I'll say plus, I don't know, 2 times x to the second. It's getting overly predictive, right? 5x, or times x right there. And then 4. Now, think about this. Now, this is going to probably catch you off guard. I need to explain this, though. Okay, so we end up with this for a derivative. It might not be what you expected. Well, what happened to the plus 4? Well, think about it. We have a 1 up here, an invisible 1 to the power of 1 for any kind of constant value here. It's not a variable. And so when you take that 1, multiply it times 4, you get 4. And then when you take 1 from the power of 1, you get 0. And when you take the 0 of something, you get nothing. It wiped it out. It's toast. It's gone. So 4 to the power of 0 is nothing. It's toast. It's wiped out. Same thing happens here. We have 1 times 5 here, right? So we get 5, but then we take x to the power of 0, it eliminates x, so x disappears. Over here, we got a bit of a similar scenario. We have x squared, right? So 2x, I'll tell you what, it'll be easier if I just take this formula, copy it real quick, over here at F5, paste it in, semicolon, shift, enter. Okay, so there you go. Now I can show you easier. Okay. And then so x squared here, so if I take 2 and I multiply it times 2, I get 4, and then subtract 1 from the 2 here, I end up with just 1 here to the power of 1 for the x. So I end up with 4x here. And then moving on, we have 3 times 3, we get 9. 1 minus the 3 here, we end up with 2. So we have 9x squared, and that gives us the derivative of, or differential equation, of our original formula. Now, we can also move on to doing this as partial derivatives, where we have multivariable calculus, or calculus 3 as it's called. And the way we do this is we hold whatever one we're doing it about as a constant. So if I want to solve for x, or about x, then I'm going to hold y as constant, and y acts as like a number would for doing this computation. So in this way, we're doing what's called a partial derivative. We can actually get 2 different answers for the same formula for taking the derivative, it just depending on which one we take it around. If we take it around x or y, it depends on which one we're doing. Here it is y, and here's x, so we get 2 different ones. How did that happen? Well, quite simple. Alright, so our original formula is 2y cubed plus 2x squared plus y plus, 2x squared times y plus x times y squared plus 2x squared. Alright, so that's the original formula. I know it's kind of complicated, but it's all getting into multivariable calculus, so we end up having 2 sets of variables, and we can solve about z or something like that. Okay, so with this, let's have a look at what we have here. Oh gosh, I wrote it wrong. No wonder. I was going, what on earth? That's why it wouldn't graph. Oh my goodness. Wow, I was sitting there going, this is not mathematically working out. Alright, hold on one second. Alright. I knew something didn't look right. Alright, there we go. I'm just real curious. We'll just plot real quick. Yep, there we go. I was wondering what was going on. Alright, that makes a whole lot of sense now. Okay. So this is a 3-dimensional plot of this curve here. That's a partial derivative in 3 dimensions. Alright. So with this, let's look at how to solve for a partial derivative on this. Okay. So, let's see here. I need to pick up where I was. Okay, yeah, so this is our original formula here. This is more what we were expecting. Okay, cool. Okay, so we're solving about x here. So the thing about this one is that x is to the first power, right? So it just gets eliminated out, and so we end up with y squared here. And that just leaves us as just like a number here would be. was about to say, that should be left behind. Alright, so plus 4x here, and again 4x is just this 2x squared here. 2 times 2 is 4, and 1 minus the 2 here, we end up with 4x here. But it's multiplied times y, so we end up with a y here too, as a constant. Plus, and then we have again 2 times 2 here gives us 4, minus 1 from the 2, we end up with 4x. Alright, back over here, same kind of idea, but we're doing about y instead. Alright, so we have our value here of 3 times 2 for our y, gives us 6. 1 minus the 3 here gives us a 2, so 6y squared. Alright, plus, let's do our next one. Alright, so since we're doing this about y, this is going to give us 2y here x. So, should be, yeah, 2xy, same thing. Same exact thing as what I said. It's just switching the order around on the variables. Alright, which you can do. It's whatever. Oh no, wait, this isn't getting evaluated. This is a constant, so this becomes y. Yes, and then that just becomes 2x squared, right? Because we're not evaluating this. That's right, we're doing it about y. So since this is just being considered a constant, there's nothing to look at. You just have y to the 1 power. 1 times 1 is 1, and then 1 minus 0 is 0 here. Sorry, 1 minus 1 is 0. So that eliminates your y and leaves you with 1 times whatever this constant value is, which is this constant value. So in this case, it's going to be 2x squared. And then this one gets dropped altogether because it has no y in it, so it's just considered a constant, so it's just eliminated altogether. And so that ends up covering this whole formula right here. Okay, good. And that is how you do a partial derivative. Alright. Here's another example of a partial derivative. It's more complex. Well, this is the formula that I put in here first. And then I do a partial derivative on it here. And then I did another formula here, and another formula here. And I've done some partial derivatives on some of these here. So you can see other types of formulas you could do, and they're partial derivatives. Just as an example of it. But it's pretty straightforward and pretty easy. The biggest thing is not to get mixed up when you're trying to do a partial derivative as to what it is you're keeping constant and what it is you're not keeping constant. Otherwise, well, it's pretty simple. But with that should cover partial derivatives and tangent to a curve from a derivative, based off an original curve, and ESUMs. It's quite a few topics. But it's all very important stuff, and we use it constantly in 3D graphics. And you'll be using this quite a bit for light algorithms and other methods that you'll be doing for 3D graphics programming. So this is vital, and it's really important that you understand this stuff. Binormals and bitangents, I believe, use partial derivatives, so it's very important that you have a good understanding of all this stuff. Alright, so with that covers all those topics. My name is Nate Nessler, and this is for Hyperactive Studios. Thank you very much.